Welcome to this problem walkthrough. In this session, we'll explore problem number 124, binary tree maximum path sum. We'll break down the problem, discuss different approaches, and work through an optimal solution step by step. Let's dive in. In this problem, we are working with a binary tree, and our goal is to find the maximum path sum. A path in a binary tree is defined as a sequence of nodes where each node in the sequence is connected to the next by an edge. Importantly, a node can only appear in the path once, and the path doesn't necessarily have to pass through the root node. The input to the problem is a binary tree, where each node contains an integer value, represented as val. The output is a single integer that represents the maximum path sum within the tree. This means we need to determine the largest sum achievable by any valid path in the tree. To better understand this, let's look at the first example. Here, the input binary tree is represented as 1, 2, 3. When visualized, the tree has a root node with value 1, and two child nodes with values 2 and 3. The maximum path sum for this tree is obtained by taking the path that includes the nodes 2, 1, and 3. Adding these values together gives us 2 plus 1 plus 3, which equals 6. So, for this input, the output is 6. Now, consider the second example, where the binary tree is represented as -10, 9, 20, null, null, 15, 7. The tree structure shows that the root node has a value of -10, with a left child of 9 and a right child of 20. The node 20 further branches into two child nodes, 15 and 7. The maximum path sum here is achieved by the path that includes the nodes 15, 20, and 7. Adding these values together gives 15 plus 20 plus 7, which equals 42. So, for this input, the output is 42. In the third example, the binary tree contains only one node with the value -3. Since there are no other nodes to form a path, the maximum path sum is simply the value of the single node, which is -3. Finally, let's consider the constraints and additional notes for this problem. The number of nodes in the binary tree can range from 1 to 30,000, and the value of each node lies between -1,000 and 1,000. When computing the maximum path sum, all possible paths in the binary tree are considered, meaning a path can start and end at any two nodes, as long as it is connected by edges. For edge cases, if the tree contains only one node, the maximum path sum is the value of that node. Similarly, if all node values are negative, the largest single node value determines the maximum path sum. Given the constraints, it's essential to compute the result efficiently, as an exhaustive exploration of all paths would not be feasible for larger trees. To begin, let's consider the brute force approach to solving this problem. The intuition here is to calculate the sum of all possible paths in the binary tree and identify the maximum among them. Essentially, for each node, we would evaluate every potential path that includes it. However, implementing this would require traversing the tree multiple times, exploring all possible paths originating from every node. This results in an exponential number of paths in the worst case, especially for a complete binary tree, making the time complexity extremely inefficient. As a result, this approach becomes impractical for large inputs and is ultimately rejected. Now, shifting to the optimized recursive approach, the key idea is to break the problem into overlapping subproblems by analyzing the maximum path sum for each subtree and propagating the results upwards. This is done using a recursive post-order traversal to compute two critical values: the maximum path sum that can be extended upwards from a node, which involves the node itself and at most one of its children, and the maximum path sum at the current node, which considers all paths starting and ending at that node, including contributions from both children. During the post-order traversal, the algorithm computes these values step by step. First, it calculates the maximum path sum from the left and right subtrees. Then, it determines the extendable path sum at the current node, which is the value of the node plus the larger of the left or right subtree sums, but only if those sums are positive. Next, it calculates the local maximum path sum for the current node, which includes the node's value plus the greater of 0 or the contributions from both the left and right subtrees. Finally, the global maximum path sum is updated whenever the local maximum at the current node exceeds the previously recorded global maximum. This ensures that the algorithm efficiently tracks the highest path sum encountered throughout the traversal. In terms of complexity, the time complexity is O, n, where n is the number of nodes, as each node is visited exactly once. The space complexity is O, h, where h is the height of the tree, due to the recursion stack. This optimized recursive approach is chosen because it effectively utilizes the properties of binary trees to compute the result in just a single traversal. By observing that the maximum path sum through a node may involve both children, while an upward extending path can only include one, we align the problem perfectly with a post-order traversal. This naturally avoids redundant computations. When comparing the optimized approach to the brute force method, the benefits are clear. The time complexity is reduced from exponential to linear, making it far more suitable for larger inputs. While an iterative approach might reduce recursion stack space, it would introduce additional complexity to the implementation. Given the constraints and requirements of this problem, the recursive method strikes the perfect balance between simplicity and efficiency. This approach seamlessly combines dynamic programming principles by reusing results from overlapping subproblems with divide and conquer by breaking the problem into smaller parts at each node. Ultimately, the decision to use the optimized recursive approach is driven by its elegance and practicality. It leverages the inherent structure of the binary tree to achieve an O-N solution, minimizing unnecessary computations and ensuring scalability. This makes it the most effective and robust strategy for solving the binary tree maximum path sum problem. Here, we're tasked with finding the maximum path sum in a binary tree. A path can start and end at any node, following parent-child connections, and must include at least one node. To solve this efficiently, we use an optimized recursive approach with post-order traversal. The key idea is to calculate the maximum path sum in a bottom-up fashion by reusing results from subtrees. We start by defining a recursive function findMaxPath, which determines the maximum sum of any path starting from the current node and extending downward. Alongside this, we maintain a global variable maxSum to track the highest path sum encountered throughout the traversal. For the base case, if the current node is null, it contributes nothing to the path, so we return 0. Then, for each node, we recursively compute the maximum path sums of its left and right subtrees, which are the building blocks for calculating larger paths. If a subtree's maximum path sum is negative, we ignore it by treating it as 0, as negative values would decrease the overall path sum. Next, we calculate the maximum path sum that passes through the current node by adding its value to the contributions from the left and right subtrees. This is expressed as path through node equals node.val plus max, 0, left, plus max, 0, right, where node.val is the current node's value, and we only include the left and right contributions if they are positive. Once we compute this, we compare path through node with the global maxSum and update maxSum if the current path is greater. Finally, we return the maximum sum of paths that can extend downward from the current node, calculated as node.val plus max, 0, left, right. This ensures that the parent node can use the best downward path sum from its left or right subtree when determining its own maximum path. The downward path sum returned is critical for the parent node's calculations, enabling the algorithm to propagate information from child nodes to their parent efficiently. After the traversal is complete, the global variable maxSum holds the maximum path sum in the entire tree. Post-order traversal is essential here because it ensures we process the child nodes before their parent, allowing us to compute subtree results before using them in parent calculations. This eliminates redundant computations and ensures each node is visited exactly once, making the time complexity linear at O(n), where n is the number of nodes. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. This approach also handles negative values by excluding paths that would decrease the sum, and it leverages a global variable and the recursion stack to manage data efficiently. Edge cases in this problem include trees with only one node, where the maximum path sum is simply the value of that node. If all node values are negative, the algorithm correctly identifies the largest single node value as the maximum path sum. For highly unbalanced trees, the recursive approach remains efficient, as it processes each node just once. Let's walk through an example. Consider the binary tree with root -10, left child 9, and right child 20, where the right child has children 15 and 7. Starting at node 15, the maximum path sum is its value, 15, which updates maxSum to 15. Similarly, for node 7, the maximum path sum is 7, so max sum remains unchanged. At node 20, the left and right contributions are 15 and 7, resulting in a path-through node of 42. This updates max sum to 42. For node 9, the maximum path is 9, and max sum stays 42. Finally, at the root -10, the left contribution is 9, and the right contribution is 35, giving a path-through node of 34. The global max sum, however, remains 42. At the end of the traversal, the global variable max sum holds the final result, which in this case is 42. This represents the maximum path sum in the given binary tree. The algorithm has efficiently calculated the result by leveraging post-order traversal, reusing subtree calculations, and ignoring negative contributions, ensuring both optimal performance and correctness. Here, we start by defining a tree node class to represent the nodes of our binary tree. Each tree node has a value, along with references to its left and right child nodes, which are initialized to none by default. Then, we define the solution class, where the maxPathSum method will calculate the maximum pathsum for the given binary tree. We begin by initializing a variable, max_sum, to -infinity. This will keep track of the highest pathsum encountered during our traversal. Next, we define a helper function that will be called recursively for each node in the tree. If the current node is null, the function simply returns 0, which is our base case. For non-null nodes, we calculate the maximum contribution from the left and right subtrees by recursively calling the helper function. To ensure we don't include negative paths, we take the maximum of the recursive resultant 0 for both the left and right subtrees. This way, we ignore paths that would decrease the overall sum. After computing the contributions from the left and right subtrees, we calculate the maximum pathsum that passes through the current node. This is done by adding the node's value to the sums of the left and right contributions. If this local pathsum is greater than our global max_sum, we update max_sum accordingly. Finally, the helper function returns the maximum contribution that the current node can provide to its parent node. This is the node's value plus the greater of the left or right contributions. Once the helper function completes its recursion, starting from the root node, we return the global max_sum, which now holds the maximum pathsum for the entire tree. Here, we start by creating a class called solution and defining a private variable maxsum to keep track of the maximum pathsum found so far. In the maxPathSum method, we initialize maxsum to integer.man_value, which ensures that any pathsum we calculate will be larger and can update maxsum. Then, we call a helper function, passing in the root of the binary tree. This helper function is designed to calculate the maximum contribution each node can provide to its parent. Inside the helper function, we first handle the base case. If the node is null, we return 0 since a null node cannot contribute to the pathsum. Next, we recursively calculate the maximum contributions from the left and right subtrees. To avoid including negative paths, we use math.max to compare the result of the recursive call with 0, effectively ignoring any subtree paths that reduce the total pathsum. Finally, we calculate the pathsum that passes through the current node by adding the node's value to the contributions from both left and right subtrees. If this current pathsum is greater than our global maxsum, we update maxsum accordingly. The helper function then returns the maximum contribution of the current node to its parent, which is the node's value plus the greater of the left or right subtree contributions. Finally, we close the helper function and the solution class. Below this, we also define the treenode class, which represents the structure of each node in the binary tree. Each treenode instance has 3 fields: val to store the node's value, left to point to the left child, and right to point to the right child. There are 3 constructors included, one with no arguments, which initializes an empty node, one that only sets the node's value, and another that sets the value along with references to the left and right children. This structure allows us to easily build binary trees and traverse them. Together, the solution and treenode classes work seamlessly to compute the maximum pathsum in any binary tree we provide as input. To solve the problem, we start with the first example, which is a simple binary tree with 3 nodes. 1 is the root, 2 is the left child, and 3 is the right child. The helper function begins at the root node, which has the value 1. Initially, the self.max_sum variable is set to -infinity, ensuring that we can correctly track the maximum path sum. The process begins by recursively calling helper on the left child, which is the node with value 2. Since both the left and right children of node 2 are none, the helper function returns 0 for both. Using these values, we calculate the maximum path sum that includes the node with value 2 as current_max equals 2 plus 0 equals 2. At this point, we update self.max_sum to the maximum of its current value in current_max, resulting in self.max_sum equals 2. The function then returns 2 plus max, 0 equals 2 to the parent node, which is the root. Similarly, we process the right child, which is the node with value 3. This follows the same pattern, with helper returning 0 for both children, leading to current_max equals 3 plus 0 equals 3. We update self.max_sum to 3 and return 3 plus max, 0 equals 3 to the root. Next, we calculate the maximum path sum at the root node, which is the node with value 1. Here, the left child contributes a maximum path sum of 2, and the right child contributes 3. Combining these with the value of the root node, we get current_max equals 1 plus 2 plus 3 equals 6. This becomes the new self.max_sum, as it is greater than the previous value of 3. The function then returns 1 plus max, 3 equals 4, which is not used any further since the root is the topmost node in the tree. The final result for this example is the value of self.max_sum, which is 6. Moving on to the second example, we analyze a tree with negative values. The root is -10, with 9 as the left child and 20 as the right child. Node 20 also has two children, 15 on the left and 7 on the right. As before, we initialize self.max_sum to -infinity and begin the recursive process. The left child of the root, which is node 9, has no children, so helper returns 0 for both. This results in current_max equals 9 plus 0 equals 9, and we update self.max_sum to 9. The function then returns 9 plus max, 0 equals 9 to the root. For the right subtree rooted at node 20, we process its left child, which is node 15. Since node 15 has no children, helper returns 0 for both, leading to current_max equals 15 plus 0 equals 15. We update self.max_sum to the maximum of its current value in current_max, resulting in self.max_sum equals 15. The function returns 15 plus max, 0 equals 15 to node 20. Similarly, the right child of node 20, which is node 7, is processed. This follows the same steps, resulting in current_max equals 7 and no change to self.max_sum, which remains 15. For node 20, we now have left_max equals 15 and right_max equals 7. Including its own value, we calculate current_max equals 20 plus 15 plus 7 equals 42. This becomes the new self.max_sum, as it is greater than the previous value of 15. The function returns 20 plus max, 15, 7 equals 35 to the root node, which is -10. At the root, the left child contributes 9, and the right child contributes 35. With the root value, this gives current_max equals -10 plus 9 plus 35 equals 34. However, self.max_sum remains 42, as it is the maximum path sum encountered. The output for this example is 42. Finally, we consider the third example, which is a simple tree with only one node, having the value -3. Here, the helper function starts at the root, and as always, self.max_sum is initialized to -infinity. Since both the left and right children are none, the helper function returns 0 for each. Using these values, we calculate current_max equals -3 plus 0 equals -3. This becomes the new value of self.max_sum, as it is greater than -infinity. The function returns -3 plus max, 0 equals -3, but since this is the root, the return value is not used further. The final result for this single node tree is the value of self.max_sum, which is -3. The time complexity of this solution is O(n), where n is the number of nodes in the binary tree. This is because the algorithm performs a depth-first traversal of the tree using a recursive helper function. Each node is visited exactly once during this traversal. At every node, we perform a set of operations, such as recursively calling the helper function on the left and right children, calculating the maximum path sums for each child, computing the current node's path sum, updating the global maximum path sum, and determining the node's contribution to its parent. All of these operations are constant time, O(1). When you combine these constant time operations with the fact that each node is processed exactly once, the total time complexity becomes O(n). This is mathematically justified by the fact that n nodes, each taking O(1) time, results in an overall complexity of O(n). The space complexity of the solution is O(h), where h is the height of the binary tree. This is mainly due to the recursive call stack, which grows in depth proportional to the height of the tree. Each recursive call itself uses constant space, O(1), to store variables like left_max, right_max, and current_max. In the worst-case scenario, where the tree is completely skewed, like a linked list, the height of the tree equals the number of nodes, n, so the space complexity becomes O(n). In the best-case scenario, where the tree is perfectly balanced, the height is logarithmic, h equals log n, leading to an O log n space complexity. Additionally, the solution uses a single global variable, self.max_sum, to store the maximum path sum, but this scalar value requires only O(1) space and does not depend on the size of the tree. Therefore, the overall space complexity depends entirely on the recursion depth, which is O(h). Let's compare this optimized solution with a brute force approach. A naive method might involve calculating the path sum for all possible paths in the tree. This would require enumerating all subtrees and their paths, leading to a time complexity of O(n²) in the worst case, since each node could be the root of a subtree with O(n) nodes. In contrast, the optimized solution avoids this inefficiency by using a divide-and-conquer strategy. It calculates the maximum path sum for each subtree in a single traversal, leveraging the results of previous recursive calls and avoiding redundant computations. As a result, the time complexity is reduced to O(n). For specific cases, like a balanced binary tree, the space complexity is O log n due to the logarithmic height, while for a skewed tree, it increases to O(n). Regardless, the time complexity remains O(n) in all cases, providing consistent efficiency. To summarize the big O complexities of this solution, the time complexity is O(n), derived from the linear traversal of all n nodes in the tree. The space complexity is O(h), where h represents the height of the tree. In the best case, for a perfectly balanced tree, the height is logarithmic, resulting in O log n space. In the worst case, for a completely skewed tree, the height equals the number of nodes, leading to O(n) space. These complexities highlight the solution's efficiency in both time and space, especially when compared to less optimized approaches. When solving the binary tree maximum path sum problem, there are a few common pitfalls to watch out for. First, it's important to account for negative numbers. While many tree problems assume positive values, binary trees can include nodes with negative values. This means the maximum path sum might exclude the root or certain branches entirely. Ignoring this can lead to incorrect results. Next, let's talk about the no-split condition. Some variations of the problem require the path to pass through the root of a subtree without splitting into left and right branches. If you mistakenly allow splits in these cases, you risk overestimating the path sum. Another common mistake is failing to optimize overlapping subproblems. A brute force approach might repeatedly calculate the same paths for subtrees, leading to inefficiencies, especially in larger test cases. Using memoization or dynamic programming can prevent these redundant calculations. Lastly, don't overlook the base case for recursion. For example, you need to return 0 for null nodes to avoid errors. Similarly, edge cases like single-node trees must be handled carefully to prevent crashes or incorrect outputs. Another potential pitfall is misinterpreting the problem's constraints. For instance, you might assume the path must start at the root or end at a leaf, even though the problem allows any node to serve as the start or end. Always read the problem description carefully to avoid such mistakes. On the topic of interview insights, it's helpful to recognize patterns. Binary tree problems often rely on recursive strategies, such as divide and conquer or post-order traversal. Mastering these techniques will make it easier to tackle similar problems. Additionally, during interviews, it's crucial to clarify constraints. For example, ask whether paths need to be contiguous, whether negative values are allowed, or whether nodes can be revisited. Demonstrating an understanding of optimal substructure is another key point. Show how the problem can be divided into smaller, self-contained subproblems, like finding the maximum path sum for the left subtree, to highlight dynamic programming opportunities. Lastly, always test for edge cases, such as empty trees, trees with all negative values, or single-node trees, as these often come up in discussions. The binary tree maximum path sum problem shares similarities with several related problems, which can help you recognize patterns and improve your problem-solving skills. For instance, problem 543, diameter of binary tree, involves finding the longest path between any two nodes in a tree. This has parallels to our problem, but with a focus on path length rather than sum. Another related problem, 437, path sum 3, asks you to count all paths in a tree that sum to a given target value. Here, instead of maximizing the sum, you're searching for specific paths that meet the criteria. Problem 112, path sum, is another example where you check if there's a root to leaf path with a specified sum. While simpler than the maximum path sum problem, understanding it helps build foundational skills for tackling more complex variations. Practicing these related problems will reinforce your understanding of tree traversal and optimization techniques. There are also alternative approaches to solving the binary tree maximum path sum problem, which can be useful depending on the variation you're tackling. One such approach is recursive DFS with single path tracking. Instead of storing all possible paths, you track only the maximum path sum at each node as you traverse the tree. This is more space efficient but requires careful handling of splits, such as combining the left and right paths with the current node. Another option is the top-down approach, where you start at the root and propagate path sums downward. This is particularly useful for variations where paths must start at the root, though it may struggle with problems that allow paths to start and end at any node. Finally, memoization is an excellent strategy for optimizing performance. By caching the results of subproblems, you can avoid redundant calculations, especially in large, unbalanced trees. The trade-off here is that it requires additional space for caching, but the efficiency gain is often worth it. Each of these approaches has its own strengths and trade-offs, so understanding them will help you adapt to different problem requirements. Great work! We've covered the key concepts and approaches for solving binary tree maximum path sum. Remember, this problem is a great example of applying recursion and dynamic programming to tree structures. Keep practicing, and feel free to revisit this explanation anytime. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!